welcome to Conversations with Matt DeLockery. In the last episode, we talked about some of the main lines of evidence to suggest that the Big Bang Theory is most likely true, which is probably why the Big Bang Theory is the most commonly accepted view among scientists. There's good evidence for it. However, not everyone has always held to the Big Bang Theory, nor does everyone hold to it today. Could there be another model of the universe that is more compelling? And if there is, could it avoid the beginning of the universe that the Big Bang Theory predicts? Today we're going to look at some of those alternative models, specifically the ones that try to avoid the beginning of the universe. Again, please remember that I am way outside of my field. I'm doing the best that I can to expose you to a line of thinking that many, including myself, find persuasive. I'm also doing my best to present only ideas that are generally accepted. Certainly, the conclusions that I will reach at the end of the series may not be accepted by some number of the scientists who came up with the theories that I'm discussing. However, I'm not relying on them for their conclusions on the existence of God. I'm relying on them for their conclusions about particular models of the universe. So everything is really put together like this. Scientists argue amongst themselves as to how the universe that we currently observe might have formed. They propose various models, and based on the merits, or not, of each model, they convince or dissuade their peers. I'm trying to relay those results to you, based on a level of knowledge that is best described as interested layman. I am not trying to decide whether one model is better or not. If I say that one is better than another, it's because the majority of scientists say one is better than another. Personally, I have no idea. So, which models have merit and why, I leave up to the scientists. I'm just trying to communicate what they say, and for whatever I get wrong, I do apologize. That's really the first half of this, communicating the scientific and philosophical information that helps point towards the beginning of the universe. The other part of this is pulling everything together into an argument for the existence of a God. That part doesn't take any special scientific knowledge. This is a philosophical argument that uses scientific data as part of its support. Remember, the argument is, whatever begins to exist has a cause, the universe began to exist, therefore, the universe had a cause. Science is used to support the second premise, that the universe began to exist. But even if I'm wrong about all the science, I've still given you two good philosophical reasons to think that the universe began to exist. However, the science that I've given you is not my conclusions. Really, it's me trying to explain the conclusions of professional scientists. So, those conclusions should still be right, even if my explanation of them could have been better. Hopefully that helps you understand a little bit better how this whole argument is put together. It's a philosophical argument that uses both science and philosophy for its support. So, now that we're done with that, let's start talking about some of these alternative models of the universe. First up is a model that I mentioned in the last episode, but that we never really talked about, the steady-state theory. With evidence from Edwin Hubble that demonstrated that the universe is expanding, it became impossible to continue to believe in a static universe, one that just sits there forever. One option to deal with the expansion of the universe was the Big Bang Theory, but there was another, the steady-state theory. This was a way to try to accept the expansion of the universe, but that still allowed for an eternal universe. The idea was that the universe was expanding, but new matter was continuously being created in the gaps left by the galaxies as they moved away from each other. Scientists were split between these two models, this and the Big Bang Theory, throughout the 50s and half of the 60s. But in the end, the Big Bang Theory just explained the evidence better. It explained better why there is an abundance of hydrogen and helium in the universe. It explained better why objects like quasars and radio galaxies were more commonly observed at large distances, which means they existed more commonly in the past than they do in the present. But the final thing that really killed the steady-state theory was the cosmic microwave background radiation that we talked about in the last episode. And that basically showed that the universe came to be in the form that it is as a result of a big explosion, or, wait for it, a Big Bang. So because of all that, the steady-state theory is basically dead today. Another possibility that was considered early on was the cyclic theory, or rather cyclic theories, because there's more than one. I'm going to just talk about the general idea, but if you want to look more into this, there are more ideas you should consider, such as membrane theory. The idea is that the universe would explode like the Big Bang, and then it would contract. Then it would explode again and then contract, and this cycle would continue on forever. So you would see an exploding and expanding universe like the Big Bang, but that wasn't the real beginning because it was doing this again and again and again forever. The problem was that the second law of thermodynamics, that we talked about 2 episodes ago, makes the eternal existence of a cyclic universe impossible. Basically, because of the second law, every time the universe goes through a cycle, every time it contracts and then expands, each expansion would get larger, meaning the universe would get bigger, and it would take a longer amount of time for it to expand and then contract again. Let me give you an example that will make this more clear. Imagine you have a rubber ball, like a basketball or a racquetball, and you drop it from eye level. What happens? It bounces back up partway, but not all the way, and then heads back to the ground. Each time it bounces up a little bit less until it eventually stops on the ground. Now imagine you have a ball made out of flubber. If you've seen the movie The Absent-Minded Professor, or the remake with Robin Williams called Flubber, you know what I'm talking about. For those who don't, imagine you had a rubber ball that did the opposite of any normal rubber ball. Instead of bouncing a shorter height, each time it actually bounced higher. Get the picture? You drop it at knee height, then it bounces up to your waist. Then on the next bounce, it goes up to your chest, then up to your head, and so on and so forth. Now, if you were to draw on a graph what the cyclic universe did, it would look like what the flubber does. The physics would be different, but the graphs would look the same. You would see a lot of bounces, and each one would be higher or larger and would take longer than the last one. Now, if you think about this for a minute, there's an implication. Suppose you saw a video of someone bouncing the flubber. And as we already discussed, each bounce is a little higher and takes a little longer. But what if you were to wind the clock back? If each bounce is a little higher and takes a little longer, then that means that each previous bounce was a little shorter and took a little less time, right? Well, if each previous bounce was a little shorter and took a little less time, then that means at some point there would have been a first bounce. The same thing applies to cyclic models of the universe. Looking into the future, each bounce takes a little longer and is a little bigger. But looking into the past, each bounce takes a little less time and is a little smaller. And if we keep winding the clock back, we'll find that at some point there was a first bounce. So, cyclic theories, instead of avoiding the beginning of the universe implied by the Big Bang Theory, they actually predict it. And so, you have a beginning of the universe. Now, we've covered 2 different models in relative depth. Let me briefly explain 2 more, and then move on to a theorem we need to discuss at length. Third on the list is the no-boundary model. Jim Hartle and Stephen Hawking proposed a model known as the Hartle-Hawking state that is similar to the Big Bang Theory, but it doesn't have the sort of beginning that we're normally used to. We usually think of the expansion of the universe sort of like a cone. The pointy end was the beginning, and the big end is now. And if you consider time moving along the length of the cone, with the pointy end being the beginning and the big end being now, then the cone represents how the universe has grown over time. Basically, what Hartle and Hawking have done is to round off the pointy end of the cone. So in essence, it's sort of like the North Pole. If you went up to the North Pole, there's a point where you cannot go any further north. But it's not like you reach an absolute point, like if you were to climb to the top of a pyramid. Their theory is really interesting, but ultimately I don't think it avoids the beginning of the universe like Hawking thinks it does. Sure, you might not be able to point to a single point, like at the end of the cone and say the universe began here, because this model removes the initial singularity, but it doesn't avoid the real problem. It doesn't give us an eternal universe. It still gives us a universe that begins to exist, because it's not eternal, even if that beginning is a little fuzzy. So even on this model, the universe still begins to exist. Finally, I want to talk about the multiverse. What if the universe that we see is only one part of what exists? What if there are lots of other universes? Well, if you think about it for a minute, this really doesn't answer anything. It only backs the problem up one step. We might ask, what kind of multiverse is it? Is it an expanding multiverse? Is it a cyclic multiverse? Is it a static multiverse? You see where this is going. all of the things that we just talked about are going to apply the multiverse. So again, all this does is really just back the problem up one step. It solves nothing. So let me explain a theorem that I think will help a lot with this discussion. It's called the Guth-Vilenkin theorem. Basically what it proves is that any universe that has been expanding, on average, over the course of its lifetime cannot be eternal in age. It must have had a beginning. So that would include the Big Bang Theory, no boundary models, an expanding universe, and even cyclic theories, because they get larger with each expansion. Remember, expanding on average. So let me read an explanation by one of the authors of the paper, Alexander Vilenkin. I'm getting this from his book, Many Worlds in One. You're going to have to think a little bit as I go through this, but as he says himself, you don't need anything more than high school math. I'll do a brief overview when I'm done reading. Okay, here's what Vilenkin says. Quote, to have a specific picture in mind, suppose there is an observer in every galaxy of our local region. Since the universe is expanding, each of these observers will see the others moving away. Galaxies may not exist in some regions of space and time, but we can still imagine the entire universe sprinkled with observers in such a way that all of them are moving away from one another. To give these observers some name, we shall call them spectators. Let us now introduce another observer who is moving relative to the spectators. We shall call him the space traveler. He is moving by inertia, with the engines of his spaceship turned off, and he has been doing so for all eternity. As he passes the spectators, they register his velocity. Since the spectators are flying apart, the space traveler's velocity relative to each successive spectator will be smaller than his velocity relative to the preceding one. Suppose, for example, the space traveler has just zoomed by the Earth at the speed of 100,000 kilometers per second and is now headed towards a distant galaxy about 1 billion light years away. That galaxy is moving away from us at 20,000 kilometers per second. So, when the space traveler catches up with it, the observers will see him moving at 80,000 kilometers per second. If the velocity of the space traveler relative to the spectators gets smaller and smaller into the future, it follows that his velocity should get larger and larger as we follow his history into the past. In the limit, his velocity should get arbitrarily close to the speed of light. The key insight of my paper with Board and Guth is that as we go into the past and approach past infinity by the clocks of the spectators, the time elapsed by the clock of the space traveler is still finite. The reason is that, according to Einstein's theory of relativity, a moving clock ticks slower, and the closer you get to the speed of light, the more slowly it ticks. As we go backward in time, the speed of the space traveler approaches the speed of light, and his clock essentially comes to a halt. This is from the spectator's point of view. But the space traveler himself does not notice anything unusual. For him, what spectators perceive as a frozen moment, stretched into eternity, is a moment like any other, which has to be preceded by earlier moments. Like the histories of the spectators, the space traveler's history should extend into the infinite past. The fact that the time elapsed by the space traveler's clock is finite indicates that we do not have his full history. This means that some part of the past history of the universe is missing. It is not included in the model. Thus, the assumption that the entire spacetime can be covered by an expanding dust of observers has led to a contradiction, and therefore it cannot be true. End quote. Okay, did you understand all of that? If this is your first time hearing it, then the answer is probably not, unless you're really comfortable with physics. I'm going to try to explain this in a shorter and hopefully more clear way. After I'm done, you might go back and listen to Vilenkin's explanation and see if it makes more sense the second go-around. Basically, what he said was that if you have an expanding universe, then everything in it will be moving away from each other, right? Now, suppose there's a space traveler going through space in his ship, with his engines off. He goes past galaxy P with a speed of 100,000 kilometers per second. And he's headed towards galaxy Q that's moving away from galaxy P with a speed of 20,000 kilometers per second, because everything is moving away from each other. Someone in galaxy Q would measure his speed at 80,000 kilometers per second, because 100,000 minus 20,000 is 80,000. You with me so far? So, because everything is moving apart, And the farther something out is, the faster it'll be moving, which means the space traveler will be going slower past every successive galaxy. The next one might measure his speed at 60,000 kilometers per second. The one after that might measure his speed at 40,000 kilometers per second. See how that works? Now, if we back things up and look in the space traveler's past, we see the opposite. The galaxy before Galaxy P, Galaxy O, might have measured a speed at 120,000 kilometers per second. Galaxy N might have measured a speed at 140,000 kilometers per second. We could keep doing this until we get really close to the speed of light, which is about 300,000 kilometers per second. Now, here's the problem. As you get close to the speed of light, time slows down. If the space traveler had been nearly at the speed of light, his time would have almost essentially stopped. So the space traveler would only be finite in age. However, we're talking about a universe that is supposed to be infinite in age. So what we have is a contradiction. This traveler, who is supposed to be traveling through the universe since eternity past, has only been traveling a finite period of time. Yet the universe is infinitely old. The space traveler cannot be both infinitely old and not infinitely old at the same time. Bohr, Guth, and Vilenkin have therefore discovered a contradiction in the idea of an eternally expanding universe. It is impossible for such a universe to exist. This means that any universe which has been expanding on average over its lifetime cannot have existed forever. Vilenkin says, quote, "It is said that an argument is what convinces reasonable men, and a proof is what it takes to convince even an unreasonable man. With the proof now in place, cosmologists can no longer hide behind the possibility of a past eternal universe. There is no escape. They have to face the problem of a cosmic beginning." End quote. So, the universe began to exist. And as we saw in the first episode in this series, whatever begins to exist has a cause. That, of course, leads us inescapably to the conclusion that the universe had a cause. In the final episode of this series, we will look at what we can know about this cause. We're not simply going to jump to the conclusion that God must have done it. We're going to look at the evidence that we already have and see if we can find some attributes of this cause. Once we're done with that, then we'll ask whether it makes better sense to call this cause a God or something else. And one final note before you go. In case you're interested, in the description I've linked to 2 videos. Both are of Alexander Vilenkin. The first is a short clip of him explaining the theory we just talked about, the one that he created with Arvin Bohr and Alan Guth. The second is the link from the full lecture that the first clip is taken from. It is a lecture in which he covers attempts to avoid the beginning of the universe and then explains why he thinks they don't work. I will warn you, though, actual knowledge of physics is required to understand these. He is not speaking to laymen like he was in his book. I'm putting them here because they represent more of the theory on which the explanation you heard was based, and because those of you who have had a lot of physics classes might be interested. So, enjoy, and we'll talk to you next week about what the cause of the universe actually is.